Okay, we're talking about how the solubility of gases is unlike the solubility of solids. For most solids, the solubility increases with increasing temperature in a finite amount of water, and namely around 100 grams of water. Whereas for gases, it's the opposite, all right? And I also mentioned because what happens with the gases, the gas particles, as they gain in energy, become more energetic, so they will escape off the surface of the liquid, all right? So, for example, on hot days, as the water level recedes in lakes, etc., you will see that fish are dying because there's less oxygen now to sustain their life. So, why could a bottle of carbonated drink possibly burst when it is left out in the hot sun? Well, what happens is there's dissolved gas in the carbonated drink, carbon dioxide. Now, as it gets hotter, the liquid gets hotter, there's going to be less of the carbon dioxide dissolved into the liquid. So all of that carbon dioxide is going to come out of the liquid and then be on top, on the surface of the liquid. The pressure inside the closed can will then increase because of the increased amount of gas there on the surface of that liquid within the can, and therefore the excess pressure would make the can explode. Why do fish die in water that is too warm? Because of the fact that oxygen is less soluble in warm water, and therefore there's less oxygen, which is why now the fish will die. So oxygen is less soluble in warm water, so it's not enough oxygen for the fish to survive. Henry's law dictates that if you have like an open can, for example, there's a little bit of carbon dioxide that will dissolve in water, but not much. However, if you apply pressure on top of the surface of that gas, then you can force more of that gas particles to go into solution. And then when you seal the can, you have a lot of gas molecules dissolved into the liquid. And then when you open the can, you're releasing pressure and all that extra gas comes out of solution. Okay. All right. Soluble ionic compounds versus insoluble ionic compounds. All right. Now, the only way those ionic bonds can be separated or broken is if the water molecule is able to separate out the ions. So the interaction between the solute and the solvent has to be quite high for the solvent, which is water, to break the ions apart. All right. As we had talked, which looked at sodium chloride before, literally water surrounds each ion, all right, so that it prevents the positive and the negative ions from coming back together. Now, there are certain compounds where water is not able to overcome this ionic interaction between the positive negative ions. In such cases, those compounds will not dissolve in water, no matter how much water you add to the compound. So, table 9.7 lists the rules of which type of ionic compounds will dissolve in water and which type of ionic compounds will not dissolve in water. So if the ionic compound contains any of the group 1 metal ions like lithium, sodium, potassium, rubidium, cesium, or even ammonium ion, then compounds of these metal ions are always going to be soluble, all right? On the other hand, if you have the negative ions like nitrate or acetate attached to any kind of metal, then they're always going to be soluble, no exceptions. Chloride, bromides, and iodides mostly are soluble except when attached to heavy metals like silver or lead or mercury. All right. So silver chloride, silver bromide, silver iodide, or lead 2 chloride, lead 2 bromide, or lead 2 iodide, mercury 2 chloride, mercury 2 bromide, and mercury 2 iodide are insoluble. Okay. Sulfates mostly are soluble except when attached to either a barium ion or a lead 2 ion or a calcium ion or a strontium ion or a mercury 2 ion. All right. So BaSO4 would be insoluble. PbSO4 would be insoluble. CaSO4 would be insoluble. SrSO4 would be insoluble, and so on. All right. So these are some of the rules, and continuing with those rules, you can see how you can apply them. So sulfides are insoluble, and so it except if you have sodium sulfide or potassium sulfide or ammonium sulfide, then they would be soluble. But mostly sulfides are insoluble. So you can see here in this picture, cadmium sulfide, it's a deep, pretty orange color. It's insoluble. Iron sulfide, which is black in color, is insoluble in water. The halides, which is lead chloride or lead iodide or lead bromide, they are insoluble in water. So lead 2 iodide is insoluble in water. Hydroxides are insoluble in water unless you have a sodium hydroxide or a potassium hydroxide or an ammonium hydroxide. So nickel 2 hydroxide is insoluble in water. And you see this green color and it comes out of solution. Barium sulfate, because of the fact that it's insoluble in water, can be used as a contrast medium. So when you give an oral dose of barium sulfate and then take an X-ray of the patient, it's used to enhance the visualization of that X-ray, especially with respect to the GI area. So sulfates are mostly soluble unless you have a barium sulfate or a calcium sulfate or a strontium sulfate or a lead 2 sulfate or a mercury 2 sulfate. So again, to recap the solubility rules, if you have a lithium, sodium, potassium, or an ammonium compound, they're always soluble in water. If you have a nitrate or an acetate compound, always soluble in water. Chlorides, bromides, and iodides, always soluble, and the exceptions are silver, lead, or mercury. Sulfates, again, always soluble, mostly soluble, unless you have barium, lead 2, calcium, or strontium sulfates, then they're not soluble. Excuse me. Sorry. Carbonates, sulfides, phosphates, and hydroxides are mostly insoluble. The only exceptions being if you have lithium carbonate, sodium sulfide, potassium phosphate, ammonium hydroxide. All right. So if these negative ions are attached to any of these positive ions, then they'll be soluble. Otherwise, they are mostly insoluble. All right, so let's apply these solubility rules and see if we can predict whether these following compounds are going to be soluble or insoluble in water. Sulfides are mostly insoluble, and so cadmium sulfide would be insoluble. Anytime you have a sodium ion in a compound, it doesn't matter what that anion is, it's always going to be soluble. So sodium sulfate is soluble. when you have an iodide, chloride, or bromide attached to lead 2, then that's insoluble. Nitrates are always soluble, no exceptions. So even though it's attached to a nickel, nickel 2 nitrate is soluble. All right. So A is insoluble, B is soluble, C is insoluble, and D is soluble. All right, so you can use these solubility rules and then determine when you are able to get a solid when two things react. And if you do get a solid, a precipitate, then you write a net ionic equation. All right, because the actual action is the formation of the solid. That's where what the reaction is. All right, and so net ionic reaction or equation shows the formation of the solid precipitate. Right, so here's an example. You're mixing lead 2 nitrate and potassium sulfate. So this is like an exchange of double displacement, an exchange of dance partners. The lead and the sulfate join up, and the potassium and the nitrate will join up. All right, so the exchange of cations and anions. Now, when the lead joins up with the sulfate, sulfates are generally soluble unless it joins up with a barium or a calcium, strontium, or a lead 2. So lead 2 sulfate is insoluble, all right? Whereas the potassium and the nitrate, they'll still continue to be soluble. So when you mix them up together, these are all the ions present, and when the lead and the sulfate join up, the lead 2 sulfate is insoluble, so it comes out of solution as a precipitate. The potassium and the nitrate still remain in solution because they are both soluble in water. So if you look at the entire reaction, the ionic reaction, all right, before you began the process of determining which would be insoluble, all of them are initially all soluble. So on the left hand side you see AQ. So when they are soluble, you will simply write AQ. The lead nitrate is soluble and the potassium sulfate is also soluble. Then on the right side, you will take those ions, which is highlighted here in red. When they get together and form a compound, they are insoluble. So they come out of solution. And so the precipitate gets the subscript of S within the parenthesis. So that indicates that that's the precipitate, whereas the potassium and the nitrate still have AQ, which means they're still dissolved in water. So essentially, the combination of the potassium and the sulfate forming the solid, that's the main reaction. All right, the lead and the sulfate coming together forming the lead 2 sulfate, that's the main reaction. The potassium and the nitrate are merely spectators to the formation of the precipitate. All right, if you eliminate those spectator ions because they occur on both sides of the equation, then you're left with the combination of lead and the sulfate forming lead 2 sulfate, which is called as the net ionic reaction. So the net ionic reaction is always going to be the formation of the precipitate, the solid. In this example, again, silver nitrate and sodium chloride, when they get together, the silver and the chloride form the solid, that's the net, and the sodium and the nitrate remain dissolved in solution. Okay, so and then you have sodium carbonate and barium nitrate. Again, the barium and the carbonate come out of solution, whereas the sodium and the nitrate remain in solution. And that's what you see in the net reaction